I guess, the first of the Greenway Online talks, and I'm really looking forward to the adaptive optics talk, which will be much more of a geek out. But you know, when we start with this picture and we just love it, you know, we love the science and we love the accomplishment and particularly the engineering, but you know, the beauty of the place just keeps overwhelming us. It didn't advance. Oh shoot, it didn't advance.
There you go.
The scope, this is a modern view of the telescope. Of course, it went into full-scale science operation in November 1949. Get an idea of the size. I think most of you have seen it already. There's a little flight suit down below the telescope that's over near the visitor gallery to give you an idea of proportion. But one thing, the fundamentals of the telescope, the gears, the drive, the mirror, a lot of the optics, these are the original telescope still in first-class operating condition. You notice all of the computer racks on the side of the cast cage. That's really a sign that it's not just the old historic telescope doing historic things. It's been modernized, it's been kept up to cutting edge standards, and it's doing cutting edge science up on the mountain today. There is an old schematic, Russell Porter from 36, I believe. It is an f3.3, largely Newtonian. I know I got chewed out for calling it a Newtonian because it does have a cast focus and bent coudes and so forth. But it's a Newtonian parabolic mirror, and f3.3 would have been relatively fast for the 1930s when it was built. Famous picture of a very modest and unassuming astronomer up there in the prime focus cage. Of course, it was originally designed for glass photographic plates, and you'd have to manipulate the plates and put them in the plate holder. That prime focus cage, which is, when the telescope is vertical, is about 80 feet above the observing floor. It's 6 feet in diameter. So you see a regular human, even a superhuman, can observe up there. I'm not sure comfortably, but successfully. Palomar's mission is science. Number one, compelling scientific investigations in astronomy and astrophysics. But you might not think of the others offhand. Facilities for astronomer training. Caltech is a research university. Lots of PhDs have been minted on this telescope and using its data. Another one that will probably become increasingly important. Think of that big, heavy, well-built telescope with excellent optics. It's good for development of state-of-the-art astronomical instruments. It's a very stable platform that can take lots of additional weight and lots of modification. So that missions like this will become increasingly important as brand new equipments that necessitate new observing techniques will be implemented on the telescope, get some science, prove the concept, and then, if necessary, scale it up for another telescope. And of course, the whole idea of the Docent program and the Greenway talks is to share the mission with students and the general public. This is Andy's slide. How historic accomplishments of Palomar Observatory. As most of you know, Palomar Observatory was really kind of designed to follow up on the discovery of that very unassuming astronomer who discovered the universe is expanding. Okay, to George Hale, not only we need more light, we need a bigger telescope because we need to nail down the expansion rate of the universe and the Hubble flow and so forth. But some other major accomplishments that are of historical nature. Alan Sandage, who was Hubble's basically protege, and Fred Zwicky really discovered that dark matter and dark energy dominate the cosmic census. So it's not just baryonic matter, atomic matter that we're all made of. It's all this other stuff that we're not sure what is physically, but we can model it and we can detect its behavior. Martin Schmidt, first spectrum of what we now call a quasar, 3C273, that led to the understanding how maybe galaxies actually form and work. They contain supermassive black holes. And of course, if you're doing a talk to the general public, everybody just loves black holes, and you can go down you can send all kinds of rabbits down that one. How about this? Willie Fowler with the Nobel Prize in Physics. Carl Sagan, we are star stuff. But he actually did the work to prove it. Elements are synthesized in stars, and there's this famous paper with Fred Hoyle and the Babbages. Elements are practically everything heavier than hydrogen, helium, and a smear of lithium are actually made in a star through one process or another. And of course, just in modern times, we just love to do the Pluto killer thing. Pluto's not really a planet. I like to do a snapshot, and this is an invalid snapshot, and it's my characterization to show that it's a general purpose telescope. It's used for a whole variety of things. There's some obvious areas of emphasis with the instrumentation, but in terms of number of nights that were programmed for March, which got discontinued, only one for engineering, work in galaxy monitoring and formation. I'm going to talk about the Zwicky transient facility, but 5 nights for follow-up on the ZTF surveys, looking at brown dwarf atmospheres, star formation itself, AGNs. We're back to the formation of galaxies and the black holes and so forth at the center, X-ray binaries, direct on black holes, compact binaries. So that gives you an idea that people like to ask us on the tour, well, what do you guys do up here? You just kind of look around. No, it's very focused work, and this is the sort of thing that's being done. All the docents know this. Of course, there's the 200-inch Newtonian, the big eye, but there is a pair of telescopes that, are very important as well. The 48-inch Schmidt telescope, which is a very wide field telescope, and it is paired with a 60-inch Ritchie-Chrétien, which was a more modern telescope built in I think the 60s. But they're paired together automatically to do wide field sky surveys at a rapid rate to discover things that go bump in the night. As Andy said, those continued to operate even during the shutdown, and now that there's some use of the 200. There's also an infrared survey following up on the techniques of the ZTF, a smaller infrared survey. I think this might be the first one in operation, and coming up soon, and Andy will know the date, they are going to augment the 12-inch with a 36-inch plane wave for these infrared surveys. How do we do it? Well, again, this is sort of for the general public again, and the big point is at the bottom. Discoveries are technology driven, right? We do science, and we do better science because we have better instruments and more accuracy and can exploit more observables. It was designed for imaging in the era of glass photographic plates. That's me. I should have used somebody else examining the plate, but sure enough, these glass photographic plates, this, by the way, is part of the Palomar Sky Survey, and they had to be reduced through all kinds of techniques. And nowadays we get digital data from our cameras that we can operate on mathematically directly. Palomar has the best instruments and software. Key tools: historically, direct imaging. Okay, take a picture of it, try to figure out what it is. Photometry, measure the variability of the light so that you can understand the underlying phenomena. In spectroscopy, kind of the queen of astronomy, you can actually detect movement, chemical composition of objects, and all kinds of phenomena. New techniques, however, adaptive optics, eliminate the barrier of the blurry atmosphere that limited the resolution of our telescopes. Network telescopes together. There is the near networking of interferometry, optical interferometry, that Andy gave us a very good talk on a few weeks ago. Yeah, it really was. Everybody ought to go back and pick that one up. But there's also whole teams of astronomers. Once ZTF discovers something, publishes, and you get a classification of 60, there are a whole series of networked observatories, ground-based, space-based, that start taking data and feed the data in. Time domain astronomy, not the deliberative techniques that we think of with photographic plates and long exposures, but very rapid astronomy, so you can detect things that have a very limited duration, and detect them very quickly too. Multi-messenger astronomy, it's already been done to some extent with radio, but now it's become a whole new field with gravity waves. The public doesn't know what photometry is, so I always like to show them this little cartoon. So there we have binary stars, and two stars side by side. There's more light. One star goes in front of the other. There's less light, but different because that one star in front is actually shining, but it goes in the back. And so you get, cartoon-wise, something kind of like this. And unfortunately, the real data looks a lot more like that. That's courtesy of Mark Lane from his master's thesis. But you can see every one of those points is a separate observation. Think of that technique in another context. This is the transit of Venus going across the sun, and you can see the light curve. You can see the sun is a little bit dark at the limbs and so forth. So if Venus transits the sun and makes an observable light curve, planets do the same around stars other than the sun. And even amateurs like Scott Dixon, if he's on board, are able to generate light curves like this for some circumstances. But the thing to really watch is look at the percentages. That Venus transit only knocked down from 100% light to 99.92. So we're talking about very exacting measurements. Come on, come on, there we go. All right. We're all amateur astronomers, or most of us. So let me turn on the video if I can get it. There you go. That's a star. We've seen this before. We struggle with it all the time. How can you do the level of science that Palomar Observatory is capable of doing, and big telescopes in general, when stars look like that, given the disruption of the waveform by the turbulent atmosphere?
Wow.
Yeah, watch it jump. Yeah, it's a great ending. So if that's the actual star size, relatively the atmosphere limited resolution is more like that big square. Okay, so you're going to lose an awful lot of detail that you can just tell visually. So you need to beat that down, and that's where advanced instrumentation comes in. The technique is adaptive optics. I'll show you a quick picture and then a little schematic about it. These were actually taken with Keck. The image on the left is one of these very blurry images of, by the way, a double star. And you might be able to see a little bit of elongation if you play with it a lot. But bingo, turn on the AO system and you get two airy disks. And
Wow.
right away, and all of a sudden you begin to do the same kind of measurements about.
Oh, you got to see this.
Pardon me? I'm sorry, I didn't get the. here's a simple diagram of an AO system. Boy, it's a lot more complicated than that, and we're all looking forward to Rick Burris's discussion of exactly how all that works. But simply, you have a reference star or an artificial star. You burned up about 5 miles of the sodium layer of the atmosphere with a laser. You have a nice waveform coming from the star, gets distorted in multifarious ways by the atmosphere. Think about a sheet of paper just, 8.5 by 11, balled up and then, thrown at the poor telescope. It gets distorted. This adaptive mirror is deformable. So it has actuators at the back of it that are computer controlled to assume a shape that would compensate for the waveform distortion in a dynamic fashion. So the waveform, it has an initial set to it. The light comes through it. There's a beam splitter. There's one lens that goes to the right and through collimators and so forth, where your science images are. Part of the light is split to a wavefront, a Shack-Hartman wavefront sensor with a lot of computing power behind it that dynamically drive that moving mirror. And the Palomar actually has more than one stage. This is very simplistic, but the mirror can be driven at 2 kilohertz. So 2,000 times a second. Probably not necessary all the time. And if you're using, by the way, if you're into magnitudes, this system without the laser works with fairly well at natural guide stars down to about magnitude 17. There it is. How about some pictures of it? Here's the same format. On the left, without the AO system, and some nice diffraction spikes too. And on the right, oh wow, airy disk and fate companion stars. So you can just tell visually without doing any math or any number crunching that through direct imaging through this AO system, we're starting to get a lot of data, and it can go a lot further. The AO system on the Palomar scope is, you would call it an extreme AO system. It's probably one of the most advanced in the world, and it's really been optimized to study exoplanet systems. So you see on the picture on the upper right, there's the AO system in the Cascade, and on the that lower monochrome picture is actually an image of a star. The star in the center, of course, the starlight would overwhelm the exoplanet, so that's been blanked out by a coronagraph. So there's a little gray hole in the middle, but actually you see this little dot with a convenient arrow, which is actually a planet orbiting another star. And if you go back to the size of that square that I showed you, there's the 0 point, plus 1 arc second, minus 1 arc second. So you can resolve that. Given this system, there are whole families of back-end instruments that have been designed to be used with it. And of course, at Palomar, nothing ever stays the same with the march of technology. It has just been recommissioned following a major upgrade. This is an older slide that I still like because it makes an interesting point. This is Project 1640 that was a collaborative effort between Caltech and the American Museum of Natural History. There's the X in the middle, that's the blanked out star. And so you see a number of planets orbiting around this host star, and you don't just see them visually, you can get an independent spectrum of each one. And if we know nothing else about them, you can tell that the atmosphere that's being reflected by the spectrometer, the chemical composition is different for each one of those little guys. This has been decommissioned and it's been replaced by an instrument called Parby that I'll talk about later. First adaptive optics fed diffraction limited spectrograph. To get diffraction limited, of course, you've got to use the adaptive optics system. And it's it is an shell spectrograph. It's a very high resolution spectrograph. And Andy knows I don't know exactly what these numbers mean because I haven't really worked the math out, but it's 100,000 resolution spectrograph, which is much higher than the other instruments at Palomar. And just by a rough comparison, the rapid spectrograph that's used to quickly classify objects that have been discovered by the ZTF, that's 100. So this is a very high resolution spectrograph using POM 3K. And the whole idea is to look for exoplanets around low mass and very young stars. And the spec is that it can detect a radial velocity, so that's toward us or away from us on the radial, of just 1 meters per second. Physically separated from the P200, however. So it's not mounted up, the spectrograph, PARVI, is not actually on the bottom next to the AO system. It's down in a separate room and connected by single mode fiber.
Oh, he's showing the presentation.
Okay. Question? Okay. Time domain astronomy. You know, I tried to make the point that although we rave about the 200 and the capabilities and the history and everything, the 48-inch Schmidt is a very significant instrument. And there's been I've got another slide about the evolution, but it is the old 48-inch Schmidt camera installed with the kind of the latest optical and electronic capabilities to do very wide surveys very quickly. So for example, you could survey the entire northern hemisphere in a single night with something like 900 revisits in a 3-year mission. You can tell, I've got a picture of people up actually working inside the telescope when it was being commissioned. And I've got another picture that actually shows the sensor with individual CCD panels that are mounted together. And of course, shim to be able to give a curved image space that a Schmidt camera would need. Some of the science objects get young supernova less than 24 hours after explosion. Fast decaying transits, particularly like brown dwarf eruptions. And yes, it's detected gravity wave transits, and so have other people too. This is an old slide, and I don't have current numbers for the third bullet. But the 48-inch Schmidt had produced these wonderful glass photographic plate Palomar sky surveys several times, and they've all been digitalized and they're available to all of us, and astronomers use them as a reference. But this new concept of the Palomar Transient Factory, which has gone from PTF to IPTF and now to the upgraded ZTF, is to link the 48-inch cadence to processing at Caltech and directing the 60-inch for a fast follow-up to characterize the observations. From one number I have is from 2009 to 2012, detected over 3,000 new supernovas, including some new types. And the public doesn't know what a supernova is, although Curtis just posted a picture of a supernova that he had taken. But so there you see the M101, the pinwheel. On the left is before the supernova eruption. And of course, we're amateurs. We know what this would look like. So bingo, a new star comes up. And once you've detected the new star with PTF, now you can get those other telescopes to join in and start taking observational data and be able to really characterize how this supernova behaves. First slide image of ZTF showing the wide field and the kind of imaging that it does. I kind of like this one. This is one that I downloaded from the site. Since I'm an amateur, I like to do it this way. But that gives you an idea of the field of view and the resolution down to about magnitude 21. Field of view, there is the ocean Schmidt telescope. So you can see to the right of the dome, you can see a little planetarium background that shows Orion. And the wide field shot that you have from Orion is the larger of the two boxes that says ZTF camera. The earlier PTF, before all these upgrades, gave you a much smaller view. You've got this very wide field view. And if you have to follow up, you can see by comparison what a Hale telescope image would look like, and then a Hubble Space Telescope image would be. So if you want to look for things that go bump in the night, use this scheme. If you want to do really fine and delicate exploitation, the other telescopes. That's a group of us up in the dome with the 48-inch before you're seeing the mirror supports. The 48 inches refers to the corrector plate, and the mirror is actually 72 inches. So that's why it looks so much bigger than you'd think. Just a couple of diagrams. Of course, with a Schmidt telescope, the imaging surface, glass photographic plate, CCD camera, whatnot, is going to be mounted inside the telescope. You can just get an idea with all the technology, original mirror, new camera, new electronics, and I'll talk about the robot, and a whole series of baffles and shutters at the bow end of the telescope to make the package. Since I'm an old refractor guy, I like to show baffles. They're the baffles. It has lots of internal baffling. And the way that filters are changed, you can see it's kind of a dilemma how one would change filters internal to a telescope. There's actually a magazine, and you can see the magazine with in a tilted direction, and an industrial robot that takes one filter off the face of the camera, puts it in the magazine, picks out another one, brings it up, and there have to be all kinds of safety latches to make this operate safely. There's a little side view of the camera, shows the magazine, it's called the filter closet here, and the robotic arm. The other half of the system, suppose you take all these images at a fairly rapid cadence, something like every 90 seconds. They get data linked to Caltech. Caltech does a significant amount of processing to discover new objects. It's kind of like the old blinking technique. Only, by the way, this whole pipeline and the software, kind of one of the new technologies that Caltech is prototyping. But suppose you have a hit, and it is an object of interest, then these objects are queued up for classification by the P60. So both these processes work automatically and robotically. The software queues up the objects for the P60 and goes and takes information for classification with this device on the back of the P60 called the SED Machine, Spectral Imagery Dispersion Machine. It's, as an engineer, I just love stuff like this because, you know, you could go overboard and have much higher resolution spectrographs that would take longer. But remember, the characteristic is time. Get through the pipeline, characterize these things so that other telescopes can exploit them. So it's got really two systems. It's got what they call a rainbow camera, which has a number of filters that you can take pictures, you know, simultaneous picture. and with different wavelengths, and you can kind of do a modest form of a spectroscopy that way. And then of course it has a separate spectrograph as well. Other advanced instruments, I don't know where Thomas is right now, but I keep it on the slides because I kind of like it. The 10 milliarc second system, these obviously go with the adaptive optics system. And there's a picture of Ganymede that it took. Ground-based picture from Palomar of Ganymede. Wow. The double chronograph, if you're going to blank out the stars, you can't just use an occulting disk with all the diffraction problems. It's really a significant problem. There's a special device, a spectral integral field spectrograph called the Cosmic Web Imager that is optimized to study filaments in the intergalactic medium and look for protogalactic disks. So the universe is still connected by these wispy relics of the original universe that are stretched out by expansion and so forth. And hydrogen is actually moving between galaxies. They actually discovered a proto-galaxy in one of these filaments. Prototyping of new imaging system, and of course I already talked about the SED Machine. CHIMERA. You know, we're all amateurs, so, you know, do you ever use a video camera with this telescope, and what would that look like? The Caltech high-speed multicolor camera, CHIMERA. I like the name, and I like the fact that if you go down to the third bullet, it uses some off-the-shelf equipment, including Canon 200mm f2L lenses, 2 of them. I can't afford one, they're about $10,000 a piece, but on the other hand, it's a lot cheaper than engineering something that's specific to this camera. And they also use a Vixen collimator as well. So it's a 40 frame per second wide field system that's basically video, and it's really designed for looking at characteristics like aurora and brown dwarfs, to monitor star fields within the Kuiper belt and look at Kuiper belt occultations and things like that. And it's planned to be upgraded to a wider field of view. But again, I don't really have any information on that at this point. Upper left picture actually shows CHIMERA up at prime focus. And the picture at the right, I think it ought to be interesting to all of us. You know how hard it is to image M1? This is a 300-second image stacked that shows a lot of detail on M1 and even some sort of a shock front coming out of the object. Come on. So what have I said? Why is Palomar important? Why is it on Sky? Great historic work that have expanded our knowledge. Pioneering design and engineering, careful maintenance, and brand new state-of-the-art instruments. These state-of-the-art instruments, I've got to emphasize, are doing science that never could have been anticipated by the people who originally designed this telescope. We all talk about, you know, maybe George Hale thought that there must be planets around other stars, but we'll never see them. And now his telescope is actually taking fairly refined data on these very objects. And if you look at the picture on the left, actually notice it doesn't have the mirror. That is, the mirror is down. The prime focus gauge is actually down and being refurbished. So you're seeing the bottom of the mirror support. Wouldn't you like to put, now again, I did this for an amateur astronomy club. Wouldn't you like to put your own camera on one of these telescopes? Well, we've done it, and it's really a lot of fun. Kind of one of the easiest things is to do a DSLR, and we've done this maybe about 4 or 5 years. Paul Gardner from Caltech started doing it to eliminate the problem. If you get a lot of students inside the 60-inch dome, it takes so long to cycle people through the eyepiece. So you can actually put an eyepiece on here. They have an old brass eyepiece that must be a Kellner. It almost looks like a tank sight. but you can put a 35 pan, you can put a 2-inch eyepiece. But so after everyone has taken their look at a planet, hopefully, or something, the cat's eye looks pretty good. Planetaries are perfect at this. Go ahead and put a camera on and project the pictures. Now, of course, we're not stacking, we're not doing anything special, but so we're very quickly taking an image 30 seconds or under with a 60-inch telescope. But here's what the images actually look like. I think focus is a little bit tricky with this rig, so I think that's M15, a little bit out of focus. You look at the ring. We got the ring in under 30 seconds. You know, it takes hours and hours and hours of data with an amateur telescope to do that. I forgot which galaxy this is. We were playing with because we could see the dust lanes and so forth. But in the upper right-hand corner, that is M87. Ooh, again, probably 30-second exposure or under, and you can actually see the jet coming off about 020 from the center. So it's a wonderful thing to be able to do things like that, and it's fun and interactive for the Caltech students. And by the way, if you ever do this with the students as docents or thing, turn the problem over to them. Don't solve it. Say, we're having trouble with this, the focus or the offset of the, and they'll jump right in and solve it. So that's my presentation.